two 12 volts battery isolator without an LTC4412. A couple of years ago I found this blog and became very excited with a solution I have been interested in for several years. Having an RV with two batteries connected in parallel, I needed a battery isolator to prevent one battery from draining the other. Also, solar panels with several batteries attached to them require such an isolator. The blog was well written and explained well how it worked. It had the circuit layout that included three P-channel IRF4905P MOSFET and LTC4412 connections for each battery. However, what struck me the most was the information that the IRF4905P MOSFET could handle up to 20 amps of current without a heat sink. According to the IRF4905P data sheet, the MOSFET is a TO220AB package, with a maximum junction to ambient thermal resistance of 62 degrees Celsius per watt, and maximum operating junction temperature of 175 degrees Celsius. As I have mentioned in my electronic circuit breaker part 5, the maximum power that a TO220 package can dissipate without a heatsink is around 2 watts, as per calculations. The IRF4905P, at VGS-10 volts and drain current of 38 amps, has a static RDS on of 20 milliohms. However, this is with a heatsink device. Without a heatsink, running at 38 amps, the MOSFET will be dissipating 28.88 watts, raising its junction temperature to 1790 degrees Celsius. It wouldn't fry, it would melt. Without a heat-sinking device, the maximum current that the IRF4905P can handle is 10 amps as per calculation. With a current of 20 amps, the IRF4905P without a heat-sinking device will fry at 8 watts, with a junction temperature of 496 degrees Celsius, as per calculation. To be able to handle the 20 amps current, without a heatsink device, a 2 watts MOSFET will need to have a maximum static RDS on of 5 milliohms, as per calculations. The other aspect of the design is that the LTC4412 power controller data sheet states that it will control the external P-channel MOSFET when it senses a voltage drop of 20 mV between the drain and source of the MOSFET. The blog mentions 50 mV drop. As it states in the LTC4412 data sheet, quote, as the sense voltage pulls up to V in -20 mV, the LTC4412 will regulate the gate voltage to maintain a 20 mV difference between V in and V sense, which is also the VDS of the MOSFET. End of quote. Well, for a 20 mV between drain and source of the MOSFET to happen, 5 milliohms RDS on MOSFET can only drive 4 amps current. That is simple Ohm's law. As the LTC4412 document also states, quote, the required RDS on can be calculated by dividing 0.02 volts by the load current in amps. End of quote. But that means a MOSFET with an RDS on of 20 milliohms or more, like the IRF4905, cannot have a current higher than 1 amp. That is basic Ohm's law. Additionally, the LTC4412 also states that, quote, if the on resistance of the MOSFET is too high to maintain forward regulation, the gate pin will maximize the MOSFET VGS to that of the clamp voltage, VG on. End of quote. However, the gate clamp voltage is around 7 volts, not the 10 volts that most of the power MOSFET requires to be driven hard and reduce the RDS onto its minimum. In summary, the LTC4412 is designed for lower current applications as it states in its datasheet. So, what is the solution? The solution is to use a MOSFET, like the LTC4412 power controller does, but using a different circuit and make the MOSFET work as an ideal diode. By using the gate voltage to turn a MOSFET on or off, based on the drain to source voltage, we can use a MOSFET, P-channel or N-channel, as an almost ideal diode. So I decided to build my own, using discrete components. Here is the circuit. I call it a differential switch, and not a differential amplifier, because there is no amplification. That is because transistors Q1 and Q2 work like a flip-flop switch. When one is on, the other is off, as long as there is sufficient voltage difference between the transistors' emitters, D1 and S1 leads in the picture. The circuit is basically a current mirror, except that the transistors' emitters are not at the same voltages, like they are in a current mirror, and the transistors' characteristics do not need to match, as it is usually the case of a current mirror. One important aspect of transistor Q2 is that its collector, marked as G1 in the picture, will be connected to the gate of a P-channel MOSFET, controlling when the MOSFET is on or off. The test circuit is designed like this. On the left we have a PNP transistor, Q1, with its emitter connected to the drain of the P MOSFET in a battery. The yellow LED was added to indicate when the transistor is on. Transistor Q1 is connected as a diode, with its base connected to its collector. The collector is then connected to the ground through a resistor. When D1, emitter of Q1, is higher than S1, emitter of Q2, transistor Q1 is on, cyan line in the chart, and transistor Q2 is off, red line in the chart. This result in G1 being at 0 volts, blue line in the chart. On the right we have another PNP transistor, Q2, with its emitter connected to the source of the P MOSFET and the other battery. The red LED was added to indicate when the transistor is on. Transistor Q2 is connected as a standard transistor, with its base connected to the base of Q1. The collector is then connected to the ground through a resistor. When D1, emitter of Q1, is lower than S1, emitter of Q2, transistor Q1 is off, cyan line in the chart, and transistor Q2 is on, red line in the chart. This result in G1 being at 12 volts, blue line in the chart. The circuit works as follows. If the voltage of the drain, 12 volts, is higher than the voltage of the source, 10 volts, the base on the left transistor, Q1, will be higher, or 12 volts minus 1 diode drop, than the base of the right transistor, Q2. In this case, the base emitter of the right transistor, Q2, will be reversed bias. The left transistor, Q1, will be on as indicated by the yellow LED which was added for the test. With its base emitter reversed bias, the right transistor, Q2, will be off as indicated by the red LED which was added for the test. With the right transistor, Q2, off, the gate of the MOSFET is low, turning the MOSFET on. The second yellow LED, close to the MOSFET, is on to indicate that the current is flowing from the 12 volts battery, through the drain, through the source, and back to ground. The LED indicates that the MOSFET is forward bias and feeding the load from the 12 volts battery. If the voltage of the drain, 10 volts, is lower than the voltage of the source, 12 volts, the base on the left transistor, Q1, will be lower than the base of the right transistor, Q2, which will have its base emitter forward bias, or 12 volts minus 1 diode drop. In this case, the base emitter of the left transistor, Q1, will be reversed bias. The left transistor, Q1, will be off as indicated by the yellow LED which was added for the test. With its base emitter forward bias, the right transistor, Q2, will be on as indicated by the red LED which was added for the test. With the right transistor, Q2, on, the gate of the MOSFET is high, turning the MOSFET off. The second red LED, beyond the MOSFET, is on to indicate that the current is flowing from the 12 volts battery, through the diode to ground, bypassing the MOSFET. The LED indicates that the diode is forward bias, feeding the load from the 12 volts battery. In the test circuit I am using a Schottky diode, instead of a second circuit. The configuration is the one you will have when isolating a battery from a wall adapter. As the drain to source voltage is mostly influenced by the MOSFET drain current, remember Ohm's law that voltage is equal to resistance times current, the MOSFET will be on, ID_M1 in the chart, and the diode will be off, ID1 in the chart, as long as the voltage between the MOSFET drain to source, VD1S1 in the chart, is lower than the voltage between the batteries, VD1D2 in the chart. The moment that the current of the MOSFET causes the drain to source voltage, VD1S1 in the chart, to exceed the voltage between the batteries, VD1D2 in the chart, the diode will be forward bias, VD2S1 in the chart, and the diode will also feed current to the load, ID1 in the chart, together with the MOSFET, ID_M1 in the chart. The simulations shows that for the diode battery to overcome the drain to source voltage, VD1S1 in the chart, and be able to turn the MOSFET off, ID_M1 in the chart, the difference of the battery's voltages, VD2D1 in the chart, have to exceed the voltage drop of the diode, VD2S1 in the chart. Even though I have not built the circuit with two MOSFET, and used a diode, instead in the test circuit, the following simulations show some of the results. The simulation below shows two IRF4905P MOSFET, with a 50 mV difference between the batteries. MOSFET M1 is feeding 10.64 amps to the load, ID_M1 in the chart, while MOSFET M2 is feeding 7.36 amps, ID_M2 in the chart, for a total of 18 amps, IRL1 in the chart. The load was chosen to keep the power of both MOSFET below 2 watts, with the drain to source voltage of one of the MOSFET at 163 mV, VD1 out in the chart, and the other at 113 mV, VD2 out in the chart. This is a difference of 50 mV. This was expected, as per previous discussions, where the MOSFET drain current times its resistance is what determines the drain to source voltage. But what happens if one of the MOSFET discharges from 100% to 0, while the other stays at midpoint, VD2 in the chart? In this case, MOSFET M2, which is the one discharging, starts feeding the load, ID_M2 in the chart, until the voltage difference of the batteries, VD1D2 in the chart, drops enough that both MOSFET contribute to feed the load, ID_M1 and ID_M2 in the chart. Then, as MOSFET M2 battery starts to discharge below MOSFET M1 voltage battery, MOSFET M1 takes over, ID_M1 in the chart. but what it is different from the previous simulation, where both MOSFET were able to contribute up to 18 amps to the load before reaching the 2 watts power limit. The difference is that in this simulation only a maximum of 10 amps can be fed to the load, so not to exceed the 2 watts power limit of the MOSFET. That was to expect, as we have presented before, that the IRF4905P MOSFET can only handle a maximum of 10 amps without a heatsink device. In conclusion, this video presented a circuit design using 2 PNP transistors and 2 resistors, plus a P-channel MOSFET, to create a simple battery isolator, which will permit two 12V batteries to be connected in parallel, reducing the possibility of one battery draining the other. It showed how the test circuit achieves the isolation between a battery and an equivalent wall adapter. It also presented the simulation of 2 batteries and 2 MOSFET, where the drain to source voltage of the MOSFET, rather than the voltage difference of the batteries, is what determines which battery will feed the load. In part 2 of this video I will present the results of the final circuit built with 4 MOSFET IRF4905P isolating 2 12V batteries installed in an RV. And that's all folks. I hope you enjoyed the video. And I thank you all for watching. Thank you.